In today's lesson, we will focus on the concept of the order of a group element. And this is an idea that's shown up in some of the in-class problems and exercises at the end of the chapter in the past. But today, we're going to formalize the idea and look into some of its properties. So let's start with an example. We'll consider the group U7, which contains elements of Z7 with multiplicative inverses. And they happen to be all the elements except 0, so 1 through 6. And we recall that U7 is a group under multiplication. And so as our first task, please pause the video for a moment and try these two questions. Find the order of element 2 in U7 and find the order of element 3 in U7. Well, let's start with part A. So in order to find the order of 2 in U7, we multiply 2 by itself many times until we get to the identity element, namely 1. So if we just multiply 2 by itself once, 2 to the first is 2, that's not the identity. 2 squared is 4, that's not the identity. But finally, 2 to the third does give us the identity element 1. And the order is the number of times we had to multiply 2 by itself, namely the exponent. And so here's a notation. This says the order of 2 is equal to 3, or we can write it this way. It's a little more explicit. The order of 2 is equal to 3. And so once again, the order is the exponent, because that exponent tells us how many times we had to multiply 2 by itself to get the identity element. So now let's go to part B. We'll find the order of 3. And so we have to multiply 3 by itself many times. Well, we'll start with 3 to the first. That's 3, so that's not the identity, so we have to keep going. 3 squared is 9, mod 7 is 2, that's still not the identity. 3 to the third is 27, mod 7 is 6, that's still not the identity, it's got to keep going. 3 to the fourth is 81, mod 7 is 4, that's not the identity. I'm going to move this a little bit over and you'll see why in a moment. Now 3 to the fifth. I suppose I could calculate 3 to the fifth, reduce it mod 7, but we notice that to get from 3 to the fourth to the 3 to the fifth, we simply multiply it by 3. And so we can do the same thing on the other side. Eases our calculation a little bit. So 4 times 3 is 12, mod 7 is 5. Not 1 yet, and 3 to the 6, again, 3 to the fifth times 3 gets us 3 to the 6 equals, same thing on the other side. So 5 times 3 is 15, mod 7, finally. So there's our desired exponent, namely 6. And so from there, we can conclude that the order of 3 is equal to 6. That's the exponent we needed to get to the identity element of 1. Or we can write it as the order of 3 is equal to 6. And that's how we do the order calculation. Now let's generalize and define the notion of the order of a group element. Please keep in mind that this definition applies to groups whose operation is multiplication, which is the default. For the corresponding definition in additive groups, please take a look at chapter 12 reading. Anyway, here it is. We'll let little g be an element of the group. Then its order is defined to be the smallest positive exponent n such that we have the relationship g to the n is the identity. And so once again, we're asking ourselves, how many times do I have to multiply g by itself to find the identity element? And we've seen these notations before. We can write this absolute value sign to mean the order of g. And perhaps a little more explicitly, we can write the order of g using this notation. Now, one quick word of caution here. Going back to that calculation in U7, we saw that 2 to the first is 2, 2 squared is 4, 2 to the third is 1. And here's where we said, aha, we have the identity element 1, so the order of 2 is 3. And that's what we found earlier, right here. But we also see that if we keep raising 2 to powers, 2 to the fourth is 2, 2 to the fifth is 4, and 2 to the sixth is also 1. But we do not say that the order of 2 is 6, even though 2 to the sixth is 1, because there's a smaller exponent, namely 3, which makes this happen. And so, as we can see in the definition, we are looking for the smallest positive exponent n. That makes g to the n be the identity, and that's why here the order of 2 is 3 and not 6. So please be careful about that. Now please pause the video and work on day 12 classwork, and afterwards we'll go over some of the problems and concepts. Let's start by discussing problem 2, where we were given a group element with order 6. And I like to ask the overarching question, for which exponent k does g to the k equal the identity element? Now you might say, well, k equal to 6 is certainly such an exponent, and that's true, but there's more to the story, so let's dig in a little further. Now we see that 6 is a divisor of 48 because 48 is a multiple of 6. Namely, 48 is 6 times 8 with remainder of 0 or no remainder. And so if we like to compute g raised to the 48th power, well, we can rewrite this as g raised to the 6 times 8. Now why do we care about 6 times 8? Because using the law of exponents, I can rewrite this as g to the 6 to the 8th power. Well, what do we know about g to the 6th? Well, the order of g is 6, so g to the 6th is identity, and then we have to the 8th, but identity to the 8th is just the identity. And so what we conclude is that g to the 48th is the identity element. And that stems from the fact that 6, which is the order of g, is a divisor of 48, and therefore g to the 48th is the identity. Now let's look at the case where we have an exponent that is not divisible by 6. So 6 is not a divisor of 263, because when we try to divide 263 by 6, we get 6 times 43 plus 5. And so we have a non-zero remainder. Here we have a remainder of 5. Now let's see what happens if we raise g to the 263rd power. Well, we get g to the, let's just use what we found here, 6 times 43 plus 5. And then again, we can break this apart using the law of exponents. This becomes g to the 6 to the 43rd power. That comes from this part. And then when we add exponents, we multiply like this, and we get times g to the 5th. Now, once again, g to the 6th, that's the identity element. And so we have identity to the 43rd times g to the 5th. And then we're just left with g to the 5th. So that tells us that g to the 263 is the same as g to the 5th. But what do we know about g to the 5th? Well, g to the 5th is not the identity element because the order of g is 6. That means 6 is the smallest positive exponent, such that g to the n is the identity. That means everything before 6 cannot give us the identity. And so g to the 5th can't be the identity. and therefore g to the 263 is not the identity. And so to kind of summarize, because 6 was not a divisor of 263, we were able to conclude that g to the 263 does not equal the identity element. So here's a theorem that generalizes the calculation that we just did. We'll let little g be a group element with order n. So in the example that we just saw, n was equal to 6, because that was the order. And the theorem states that if n is a divisor of k, if and only if g to the k is equal to the identity element. So for instance, we just saw the case where the order of g was 6, and we saw that because 6 is a divisor of 48, g to the 48th was the identity. And because 6 is not a divisor of 263, g to the 263 was not equal to the identity. And so to summarize, only the order of g or its multiples satisfy g to the k equals the identity element. And so we're going to talk about the proof of this theorem, and I'll start by pointing out that this is an if and only if statement. So there are two implications we need to prove, namely, if n is a divisor of k, then g to the k is equal to the identity, and also its converse, namely, if g to the k is the identity, then n is a divisor of k. So a couple of remarks here. We're going to prove the second implication in this class. This is, I think, the more difficult implication, so let's do it together. Another comment I'll make is that in the classwork, in particular in problem 6 in classwork, you actually prove the contrapositive of this second implication, namely, if n is not a divisor of k, then g to the k doesn't equal the identity element. And so that was in problem number 6 of the classwork. So we've already proven this once, but I like to prove the original version without resorting to its contrapositive. And so that's what we're going to do next. Now, before we prove the second implication here, we're going to take a quick detour and talk about problem 4, because that's going to introduce a useful tool that we'll be using to prove the second implication and also many other theorems in this class. And so here's problem 4, where our friends are asked to find the remainder when dividing 263 by 6. Now, Elizabeth claims that the remainder is 11 because 6 times 42 plus 11 does equal 263, except calling 11 the remainder isn't quite right because we can take out another copy of 6 from 11, so that remainder feels a little too big. Now, Anita says that the remainder is -1. Now, 6 times 44 plus -1 does equal 263, but we've pulled out too many copies of 6 because our remainder shouldn't be negative. And so if 42 copies of 6 isn't enough, 44 copies of 6 is too much, then certainly the correct number of 6s is 43. And so 6 times 43 plus 5 does equal 263, and indeed 5 is the correct remainder that we want. And so here's a theorem that generalizes this particular example, and it's typically called the division algorithm with the integers. And so we'll let a and b be integers. If you like, think of a as 263 and think of b as 6. And we'll assume that b is positive. And we're going to talk about remainder when we divide a by b. And so the theorem says if we have the integers a and b, with b being positive, then there exists a pair of integers q and r, q for quotient, r for remainder, such that a is equal to b times q plus r. And the focus here is this restriction that we can guarantee on the remainder, that we can always choose the remainder such that it's less than b, the number that you're dividing by. So in this case, 5 is less than 6, and also non-negative. And so this theorem guarantees the existence of the quotient q and remainder r, and oftentimes remainder r is one that's going to play a role, and we can put a restriction on the remainder. And so just a couple of remarks about this theorem. Once again, in words, the remainder r must be less than the divisor, and so that would be b, and also non-negative. And this division algorithm is often very helpful in showing that an integer n is a divisor of k. Very briefly, the way we use this division algorithm theorem is that we try to divide k by n and show that the remainder is 0. And so we'll see how to use that in our next slide. Now we're going to prove the following theorem. Let G be a group element with order n. And we're going to prove the claim, if G to the k is the identity, then n is a divisor of k. So this is the second implication from our earlier if and only if statement. Now, one of the reasons why I like to go over this particular theorem and its proof is to introduce a proof technique, namely, how do we show that n is a divisor of k? An integer is a divisor of another integer. And so that's our next proof know-how. To prove that n is a divisor of k, in a nutshell, we try to divide k by n and show that there is no remainder 0. And so more precisely, we can use the division algorithm to write k is equal to n times a quotient plus a remainder with this appropriate restriction on the remainder. And then we show that r is 0, because then this term goes away. We're left with k is n times q, and therefore n is a divisor of k. And so applying that particular proof technique to this theorem right here, I'll describe the proof outline first, and then we'll go through the complete proof. And so how does the outline go? Well, the first thing we know is that n is the order of G. What does that mean? Well, that means that n is the smallest positive integer such that G to the n is the identity. Now, in our proof, what we're going to show is that G to the r, where r is the remainder, is also equal to the identity. But r, we know, is less than n. And n is supposed to be the smallest exponent, such that G to the n is the identity. How is it possible that G to the r is also the identity? Well, here's the key point here. N is the smallest positive integer, such that G to the n is the identity. So if G to the r is identity, r must not be positive. Well, what do we know about r? It's less than n. We already used that. It's also non-negative. But we also know that r isn't positive. Well, the only integer that's neither negative nor positive is 0. And that's how we conclude that r must be 0. So once again, we're using the fact that r is less than n to say, well, the only way this is possible, n still being the order of G, is that r is not positive. But r is not negative either, and therefore r must be 0. And so that's going to be the proof outline. In the next slide, we'll go over the complete proof. Here's the proof of our theorem. Let's state it again. Let G be a group element with order n, and if G to the k is the identity, that's our hypothesis, then n is a divisor of k. And so as usual, we've already put the hypothesis up top. We'll assume that G to the k is the identity. And then our very last line, therefore, n is a divisor of k. And so just to help guide our proof, we must show that n is a divisor of k. Now let's proceed as we did in our outline, namely, in order to show that n is a divisor of k, we'll try to divide k by n, and we'll show that the remainder is 0. And so here it is. Using the division algorithm, we'll write k is equal to n times q plus r, where q and r are integers, with our restriction on the remainder. And our goal is to show that the remainder r is 0. Now, next step. Well, we already know that G to the k is the identity, and so let's use that expression for k and substitute it into k. And so since G to the k is the identity, we can write down replacing k with n times q plus r, we obtain G to the n times q plus r is equal to the identity. Now, what do we know? Well, we also know that because the order of G is n, that G to the n is the identity as well, and that's going to play a role. And so there are some technical details here that I'll ask you to fill in, or you can look at the chapter 12 reading. But I'm just going to skip a little bit and cut to the chase. You can show from here, and then using what you know about n, to conclude that G to the r is the identity. Once again, I'll leave those technical details to you, or you can take a look at the chapter 12 reading. But G to the r is the identity. What can we say? Well, we know that r is less than n because r is the remainder. But we also know that n is the order of G. In other words, n is the smallest positive integer such that G to the n is the identity. Well, how's that possible? R can't be positive because that would contradict the fact that n is the order of G. R can't be positive, but we also know that r being the remainder is greater than or equal to 0. So the only possibility is that r is equal to 0. And therefore, with the remainder gone, we can write k is equal to n times q, and therefore n is a divisor of k. And so I wanted to go over this example. It is an important result about the order of an element, but also it's an example of how we can show that n is a divisor of k using this new technique of the division algorithm. And so with that, that's the end of our proof and also the end of our lesson. And I will see you next time.